Okay, in this problem, we've got a non-linear spring, so we're not going to follow Hooke's law, okay, which would be a linear spring, okay? And I have a tensile force deflection relationship to the force given by that equation there, where x is meter and newtons. It wants me to find the acceleration when I pull the 6 kilogram block back 50 millimeters and then 100 millimeters, okay? So let's go ahead and we'll draw our free body diagram here. Okay, so I've got my block right here. Okay, I'm gonna have 6 times 9.8. Okay, because 6 kilograms, I need it in newtons. Okay, I'll then have a normal force acting straight up, right? I have my spring force, which is not K times S, it's that equation that I have up there. For right now, I'll just call it F sub S. Okay, and then I've got friction, and again, that friction is going to oppose um, that spring force. So I'll draw my friction going to the right. So we're going to use our standard XY axes like this because my acceleration is going to all be in the X direction, right? It's only going to accelerate horizontally here. So we'll go ahead and sum our forces horizontally, okay? And I've got my friction force minus my spring force, and that's going to equal the mass times the acceleration. And that's really what I'm trying to find is that acceleration. The mass, of course, is 6, and the acceleration is a. Okay, that I'm trying to figure out what that is. Okay, I'll now sum the forces in the y direction, and in the y direction I've got n, and I've got 6 times 9.8 acting straight down. There will be no acceleration in the y direction. That's why I set this up this way. I know all of my acceleration is in the x direction. So from that, I can determine that my normal force is 58.8. And this is going to help me deal with my friction as we go through here. So what I'm going to do is I'm going to basically find the point at which it'll start moving, right? Because if I pull it back just a small amount, it's not going to snap back. I want to figure out where that happens to see where I may actually get some acceleration. Okay, so I'm going to start by assuming equilibrium. Okay, where essentially my acceleration will equal 0. Okay, so when my acceleration equals 0, then I know my friction force equals my spring force. Okay, and if I'm trying to find that point at which it just starts moving, basically right before friction gives up the ghost. So I'm at that max friction, which I'm going to call 0.3 times 58.8. That's mu s times n. This is the maximum friction force. Okay, so this is the point at which friction can no longer hold. Okay, and I'm going to set that equal to 150x plus 400x, which is the force of this nonlinear spring here. Okay. From this, I can determine that my x is 0.094, which is 94 millimeters. Okay, so because of that, anything less than 94 millimeters, friction is going to keep that in place. So from that, I know that the acceleration when x equals 50 is going to equal 0. Okay, but when x equals 100, it it will start moving. Okay, friction can't hold it. This is the max amount that friction can hold. So any more than 94 meters I pull back, this thing is going to accelerate. So at 50, it will just stay where it is. At 100, okay, now I know my friction force will be the mu k times n. So I take that friction force, and this time I'll call it 0.25 times 58.8 minus my friction. I'm sorry, not my friction, my spring force, which is going to be 150 times 0.1 plus 400 times 0.1 squared. Okay, and that's going to equal 6a. So again, at this point, I know it's going to be moving. I know that the spring force can overcome that friction. So from that, then I go ahead and calculate what that acceleration will be at that instant. And I can go ahead and calculate that, and I get a equal to negative 0.717, and that will be meters per second squared. Negative is because it's traveling in the negative x direction. That's to the left, right? I defined X to be positive to the right. So the negative sign just tells me, hey, that thing's accelerating to the left, which makes sense. It's the spring pulling it back. So that's what's causing that acceleration.